Hello everyone. Today's presentation is on robot dynamics, Euler Lagrange Formulation, and general Matlab code. The outline of the presentation is joint velocities of robot manipulator, effect of joint motion on other links, kinetic energy, potential energy of the robot manipulator, equations of motion of the manipulator, dynamics of a two-link manipulator, generalized code for inverse dynamics in Matlab, and its validation. Let R be a fixed point in link I, and this point R with respect to ith frame, which is also present in link I, can be defined by this point xi, yi, zi and 1, which is for homogeneous transformation purpose. It can also be represented in this form. This point R, which is in ith frame, can be transformed with respect to base frame with the help of this transformation matrix. This transformation matrix is nothing but a multiplication of other matrices, which are also transformation matrices. The general form of transformation matrix: if joint I is revolute, then this is the matrix. If joint I is prismatic, then this is a transformation matrix. Now, the velocity of that point, which is on link I, is given by d by dt of R with respect to base frame equal to d by dt R with respect to ith frame and this transformation matrix which converts that point to the base frame. And this transformation matrix is actually the multiplication of other transformation matrices given here. And when we substitute this here and when we differentiate with respect to time, we get this expression. And we find that the last term in this expression actually is 0 because we are differentiating point R, which is present in link I, with respect to ith frame. So that value is 0 because that distance does not change. This is possible only for a rigid body, and in case of flexible bodies, this term is not 0. This whole expression can now be written in this form. Now our area of interest is this circled term, which is partial derivative of the transformation matrix with respect to a generalized coordinate. It is a generalized coordinate because it can be a revolute joint or a prismatic joint, so it can be an angle or it can be a displacement. Now how do we find the partial derivative of this transformation matrix with respect to this generalized coordinate? It is found that this value is actually equal to this transformation matrix multiplied by another matrix, which is this matrix for rotary joint and this matrix for prismatic joint. Now let us see how did we get this value of this matrix Q. If we compare the transformation matrix for a rotary joint, that is Qi is theta I, this is the transformation matrix, and this is its partial derivative with respect to theta I, that is cos theta I, the derivative is minus sin theta I, minus cos alpha I sin theta I, the derivative of this term with respect to theta I is minus cos alpha I cos theta I. In this case, alpha is treated to be constant. Now when we compare these two matrices, we find that the second matrix is actually a multiplication of the first matrix with this term. For example, let us consider the first row of this matrix and the second row of this matrix. The terms, elements of this matrix, the elements of this row are same. And that is why we have a 1 here. And if we see in the second case, the second row, this row is actually multiplied by minus 1 and then we get this row. And this minus 1 in this matrix is because of that. So hence we get this Q matrices by comparing these two. This is the final Q matrix, which is different for rotary joint and prismatic joint. Now this partial derivative of transformation matrix with respect to generalized coordinate can be expressed in this form for j less than or equal to I, that is number of joints are less than or equal to number of links, and is 0 if the joints are more than links. If the joints are more than links, then that joint has no effect on the link. Hence it is 0. Now we define a new term Uij to actually represent partial derivative of the transformation matrix with respect to generalized coordinate. And Uij is this expression for j less than or equal to I equal to 0 for j greater than I. We define another new term Uijk, which is nothing but partial derivative of the previous term with respect to Qk. That is, we are actually trying to get the interaction between two joints on a link. In this case, I is link, J is a joint, and Q is a joint. So, this expression, when we differentiate it with respect to Qk, we get this expression. And while differentiating this expression, we can use the property that the partial derivative of transformation matrix with respect to generalized coordinate is actually Q times the transformation matrix. So we get 2 times Q here. Let us consider an example for a robot arm. For a single arm, number of links I is 1, number of joint is 1, and for comparison, there is another joint. The total joint is actually 1. This is considering the effect of other joint, which is also 1. There is no second joint. So partial derivative of u11 with respect to theta 1 is nothing but this expression. And when we expand this, we actually get q1 dot, then partial derivative of this plus q1 partial derivative of 0 or t1. The derivative of q1 is 0 because it is a constant, and partial derivative of this transformation matrix is nothing but the transformation matrix multiplied by q1. Therefore, we get 2 q's. Let ki be the kinetic energy of the link and dki is the kinetic energy of a particle with differential mass dm in link I. Then dki is given by this expression, which is nothing but half xi dot square plus yi dot square plus zi dot square dm. Kinetic energy we know is that it is half mv square, and v is nothing but square root of this expression. So v square is xi dot square plus yi dot square plus zi dot square. Now how do we get these values? For example, we know that this point r can be defined by xi, yi, zi 1. So when we multiply by r again, we get a term similar to this matrix, where xi square, yi square, zi square are actually the elements of the diagonal. And now that we have these terms, the sum of these terms will actually satisfy here. So this is nothing but the sum of the diagonal elements is nothing but the trace of the matrix, which is equal to half trace vi transpose dm. If this is r, v will be xi dot yi dot zi dot 1. Sorry, here it is 0, and when we multiply again with xi, yi, zi, we actually get this matrix, and the sum of diagonal elements will actually give us the value of this term, which is nothing but trace. Now this kinetic energy can now be rearranged in this form. This term is vi and this term is vi transpose. It can be rearranged to this form, and now the same thing can be rearranged finally into this. Here we find a term r, m, r, which is nothing but mr square. Mr square is nothing but moment of inertia. So summing up of kinetic energies of all links is nothing but integral dki equal to half trace of this expression. And in this expression, we find that this value, which is nothing but r transpose dm, is actually given by inertia tensor. Inertia tensor is a matrix which actually gives the idea of moment of inertia of the 3D object when it is rotating with respect to different axes. And this inertia tensor can also be expressed in this form, where Ixx, Iyy, Izz are the moment of inertias about the principal axis. And this inertia tensor can also be expressed in this form, where k is the radius of gyration. This inertia tensor is different for different bodies, and based on the type of manipulator link, we can find out this inertia tensor matrix. The total kinetic energy is nothing but sum of individual kinetic energies of every link, and this is the final expression which we get. Now, the potential energy of each link is given by mg into this distance from the zero base position or the relative position. So, which is nothing but mig into r, and this r with respect to base frame can be written as r with respect to ith frame of link I multiplied by this transformation matrix. This is for a single link, and potential energy of all links is equal to the sum of individual potential energies, which is nothing but this expression. Lagrangian is nothing but total kinetic energy minus total potential energy, which from previous equations, if we substitute here, we get this equation. Now, applying Lagrange equations, that is tau I equal to d by dt partial derivative of Lagrangian by qi dot minus partial derivative of Lagrangian with respect to qi, we get this expression. When we substitute L here, partial differentiate, we get this. And this term can be grouped as this equation, where D represents the inertial terms, H represents the Coriolis and centrifugal terms, and C represents the gravity terms. The same thing is expressed here in detail, where D represents the inertial term, H represents the Coriolis and centrifugal force vector, and C is the gravity load force vector. Let us consider the example of a two-link manipulator. The joint variables are θ1 and θ2, that is revolute joints. Mass of the links m1 and m2, and the length of each link is L. This is the transformation matrix for first frame with respect to base frame, second frame with respect to first frame, and this is a transformation matrix for second frame with respect to base frame. Q in this case is this matrix because it is revolute joint. U11 is given by this expression, which is nothing but partial derivative of transformation matrix with respect to θ1, and it is given by this matrix. Similarly, we find U21 and U22. Assuming all the products of inertia as 0, the inertia tensor for first link is this, and the inertia tensor for the second link is this matrix. And this matrix is for a link which is assumed to be slender. Slender means the length is more than the other two dimensions. That is, the other two dimensions are very small when compared to length. For this, one can refer the inertia tensor of a rectangular link or a rectangular object for this matrix. Now, we find D11, which is given by this expression. That is, we multiply these matrices and then find the trace. Trace is nothing but the sum of diagonal elements. Similarly, we find D12 and D21. And similarly, we find D22. All these terms, D, are nothing but the inertial terms. Now, we find the Coriolis and centrifugal terms. We have discussed this in the previous slide, and substituting 1 and 2 in the generalized equation, we get H1 and H2. And this is the H matrix. Similarly, C1 is a gravity term and also C2. C1 is obtained by substituting 1 in the generalized equation discussed earlier. This is a final matrix for gravity terms. Combining all these, we get the final torque equation, which is nothing but the inertia matrix. This is the Coriolis and centrifugal matrix, and this is the gravity matrix. Let us discuss the generalized code for inverse dynamics of the manipulator. Clear all, clears workspace, figures, command window. Format, which is of bank type, that is 2 decimal places. Global variables nj, nf, dof, theta. Global variables because these variables are called for many functions. We are reading the file dhparam.txt, which actually has the dh parameters of the two link. So this is the dh parameter, alpha, a, d, theta, dq by dt, and flag. This flag is 1 for revolute joint and it is 0 for prismatic joint. Though we have given theta and dq by dt to be zeros here, we have actually considered those values which is discussed in the program later. After reading this DH parameter file, we perform this operation fscanf. Fscanf actually reads the file values and positions file pointer at last read value. That is, say for example we are reading this text file. It reads the value present in the first row, and next time when we call this function again, it reads the value in the second row. This is the gravity matrix. Gravity is in negative y direction. XLS read actually opens the Excel sheet, which is our source file here. Let us see what is there in this source file. Here we have the time values. We have the coordinates for the starting of first link, ending of first link or the starting of second link, and the ending of second link. From these coordinates we get θ1 and θ2, and from θ1 and time we can get θ1 dot and θ2 dot using a Matlab code, and we can get θ1 double dot and θ2 double dot. Sometimes these values θ1 and θ2 are directly given to us. In that case we don't require these coordinates. Now BC gives the rows and columns value of this matrix or of this Excel sheet, which is read. We are inputting or reading another text file which has the geometric properties of the link, that is geometric var.txt. Here we have given the mass of the two links. Say they are 7 units and 3 units. Length, width and height both are 0 for slender link. XC minus 0.25 and minus 0.25. This is negative because for every link its frame is fixed at the end of the link. So when we want to know the center of gravity, because the frame is fixed at the end of the link, you have to come minus 0.25 units in the negative direction, because the length of that link is 0.5 units. And this is the same for both the links. FID is minus 1. It says file not found. This is a standard used in Matlab. NJ is number of joints. For the first link and the second link, we actually read these values: mass, length, width, height, and center of gravity. This is the moment of inertia of the link which we have considered about the principal axis. This is the generalized inertia tensor. This matrix changes if the link is cylinder or of any other shape. The coordinates of center of gravity. Now for I equal to 1 to B, B we know that is the number of rows of that source file which we are referring. Alpha, A, theta, D and flag we get from this file, DH parameter file. So in this DH parameter file, as discussed earlier, theta and dq by dt are given as 0. However, those two values are actually inputted to get the torque values. dq is velocity, d2q is acceleration, and this actually referring to the Excel sheet which we are reading, and the values are taken from that Excel sheet. Alpha is read from the file, A is read, D of k is read. For the first link, that is if k equal to 1, theta 1 is nothing but this value plus Ti of 8. Ti of 8 is the value present in the 8th column. If it is link 2, then we are referring to the 11th column. These two values are actually 0 because We have not mentioned any value here. We are taking these values from the Excel sheet. And if k equal to 1, dq by dt, that is velocity, is taken from the 9th column, and k equal to 2, that is if it is the second link, it is taken from the 12th column. If there are other links, like say 3 links, then k equal to 1, else if k equal to 2, else the third link. This is the transformation matrix for prismatic joint, transformation matrix for revolute joint. This T concatenate function actually concatenates the matrices. If we want to find the end frame with respect to the base frame, we actually have to multiply many matrices, and this function does it. And dA2 is derivative A2 flag j. Let us see what is there in this derivative function. So as discussed earlier, if we want to find the derivative of a transformation matrix, we actually have to multiply by Q. And this is the matrix if it is rotary joint. This is the matrix if it is prismatic joint. This term actually means that the first row of dA is minus times the second row of A matrix, and the second row of dA is equal to first row of A matrix. So that can be verified by seeing these matrices, matrix rows and columns. If it is prismatic joint, we find that in third row and fourth column there is 1 present, because for a prismatic joint only this matters and the angles do not matter, because it remains constant, the differential is 0. Third row, fourth column of dA matrix is actually equal to third row, fourth column of the A matrix. So this term represents that. Once the matrices are concatenated, then we find UU, that is, which we have discussed in slide number 8 of the presentation, which actually refers to the effect of joints on the links. dA2 refers to effect of joint on a link, and UU actually is the interaction forces between two joints, or the effect of joints on a single link. D is the inertia matrix, which is obtained from the expression discussed in slide number 14 of presentation. The Coriolis and centrifugal terms, which is represented by H. The gravity terms represented by C. So till here, this complete code is actually the generalized code for inverse dynamics of a manipulator, and this is using Euler Lagrange method. To validate this code, which is highlighted in blue, we have also written this expression which we got directly from for a two-link manipulator. So the above code is the generalized code, and this part of the code is the torque equation for a two-link manipulator, and this two-link manipulator with revolute joints. And this expression can also be referred in slide number 25 of presentation, which is similar to the expression in the book, Foley and Gonzalez. This is the final expression of torque. GI1 gives torque 1 from the generalized code. GI2 gives torque 2, that is torque at joint 2, using the generalized code. Similarly, GI3 and GI4 gives the torque values for the two-link code here. That is, GI3 and GI4 are nothing but this T1 and T2. Now let us verify whether GI1 torque 1 and GI3 torque 1 for the specific two-link are matching. And similarly, this torque 2 from here and this torque 2 from here have to match. Let us run this code. For example, let us take G 10, 1. I can be anything, which is minus 106.91. Now, this is torque 1 using the generalized code. Let us see what is torque 1 using this expression. So we have to check for G 10, 3. Both G10, 1 and G10, 3 are minus 106.91. This verifies that the torque values obtained using generalized code and the torque values obtained using the specific two-link code are same. Acknowledgement, references. Thank you.